You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Robotics is the branch of artificial intelligence that extends beyond software into the physical world, where machines are designed to sense, decide, and act. Unlike purely digital systems that process data and generate outputs on screens, robots embody intelligence in physical form. They must perceive their surroundings, plan movements, and carry out actions that interact directly with people, objects, and environments. This makes robotics one of the most complex areas of AI because it combines vision, control, reasoning, and mechanical engineering into a single integrated system. A robot in a factory must detect parts on a conveyor belt, calculate the best path to pick them up, and precisely place them into assemblies, all while adapting to variations in speed and position. For learners, robotics demonstrates how AI moves from abstract algorithms into tangible action, showing the challenge of bringing intelligence into the messy, unpredictable real world. The roots of robotics stretch back centuries, long before the modern concept of AI. Early inventors created mechanical automata, intricate clockwork machines designed to mimic human or animal behavior. These devices could write, play instruments, or simulate lifelike movements, though they operated entirely on fixed mechanical principles. The 20th century saw the rise of programmable robots, especially in manufacturing. Unimate, introduced in the 1960s, became the first industrial robot arm, revolutionizing assembly lines by performing repetitive tasks tirelessly and precisely. These early robots were not intelligent in the modern sense, but they established the foundation for integrating programmable control with mechanical systems. Over time, advances in computing and sensing technology brought the possibility of embedding real decision-making into robots, shifting the field from rigid automation toward adaptive AI-driven machines. Sensing is at the heart of robotics, because without perception, machines cannot respond meaningfully to their environment. Robots rely on a range of sensors, each capturing different aspects of the world. Cameras provide visual data for detecting objects and navigating spaces. Lidar, which uses laser light to measure distances, creates detailed 3D maps. Radar extends perception to poor weather conditions, and touch sensors provide information about pressure, texture, and contact. Together, these sensing systems give robots a multi-layered view of reality. For example, an autonomous vehicle may use cameras to detect traffic lights, lidar to map nearby cars, and radar to track movement in fog. The integration of these diverse sensors enables robots to operate in varied and uncertain conditions, but it also introduces challenges of combining noisy, incomplete, and sometimes conflicting data into a coherent understanding of the world. Perception in robotics is never straightforward. Sensors produce data that is often noisy, partial, or ambiguous, requiring interpretation before it can guide action. A camera might misread shadows as obstacles, lidar may fail to detect transparent glass, and microphones can pick up irrelevant background noise. The environment itself adds complexity, as conditions shift dynamically with changing light, weather, or human activity. For example, a warehouse robot may see neatly stacked boxes one day and cluttered aisles the next, requiring it to adjust navigation strategies. Handling such uncertainty requires advanced algorithms that can filter data, identify reliable patterns, and update interpretations on the fly. This challenge highlights the difference between sensing and true perception. Gathering raw data is relatively easy, but making sense of it in real time is the demanding task that brings robots closer to human-level adaptability. Motion planning is another essential component of robotics. Robots must not only know where they are, but also determine how to move from one point to another safely and efficiently. Motion planning algorithms calculate paths through environments, avoiding obstacles and optimizing routes. For instance, a warehouse robot planning to pick an item must decide how to maneuver around shelves, workers, and other robots. Path planning combines geometry, probability, and optimization, often under time pressure. Beyond simple navigation, motion planning also applies to manipulation, such as a robotic arm deciding how to grasp an irregularly shaped object. The complexity arises from the near-infinite number of possible paths, requiring clever approximations and heuristics. For learners, motion planning illustrates how robotics translates goals into actionable sequences, balancing efficiency with adaptability in environments that rarely remain static. Kinematics and dynamics form the mathematical backbone of robotic movement. Kinematics deals with geometry, how joints, arms, and wheels are positioned and oriented in space, while dynamics considers the forces and torques that drive those movements. For example, a robotic arm reaching for an object must calculate the angles of each joint to position its gripper correctly, while also accounting for the weight of the object and the friction in its motors. Kinematics ensures the robot moves where it intends, and dynamics ensures that it moves safely and realistically without exceeding physical limits. These mathematical models allow robots to execute movements that appear fluid and precise. For learners, kinematics and dynamics reveal the deeply interdisciplinary nature of robotics, blending mechanical engineering with AI planning to achieve coordinated, real-world action. Control systems ensure that robots can adjust their actions in response to changing conditions. A control system is essentially a feedback loop. Sensors monitor the robot's state, compare it to a desired goal, and adjust motor commands to reduce errors. Consider a drone hovering in mid-air. Sensors measure altitude and orientation, and if the drone drifts off target, the control system quickly corrects its thrust to maintain stability. Without such feedback, robots would be brittle, unable to adapt to disturbances or errors in planning. Control systems allow robots to be both precise and resilient, bridging the gap between theoretical plans and practical execution. They illustrate how intelligence is not only about high-level reasoning, but also about constant, low-level adjustments that make behavior robust in the physical world. Manipulation is one of the most iconic tasks in robotics, involving robotic arms, grippers, and hands designed to handle objects. In manufacturing, robotic arms assemble cars, weld parts, or package goods with high precision. Beyond factories, robotic manipulation extends into household tasks, like folding laundry or preparing food, though these are far more challenging due to the variability of objects. Grippers range from simple two-finger claws to sophisticated multi-fingered hands that mimic human dexterity. Tactile sensors provide feedback about grip strength and texture, enabling robots to handle delicate items without damage. Manipulation highlights both the promise and difficulty of robotics. Simple, repetitive motions are solved, but general-purpose handling of arbitrary objects remains one of the great open challenges in AI-driven robotics. Mobile robots expand robotics into locomotion, enabling machines to move across varied terrains. Wheeled robots dominate warehouses and factories, where smooth floors make rolling efficient and reliable. Legged robots, inspired by animals, tackle rougher environments, climbing stairs, or walking over uneven ground. Flying robots, or drones, provide aerial mobility, supporting tasks like surveying, delivery, and search and rescue. Each form of mobility comes with trade-offs. Wheels offer stability and efficiency but struggle in complex terrain, while legs provide adaptability at the cost of complexity. Drones provide speed and access but face challenges in energy efficiency and payload. For learners, mobile robots illustrate how different designs emerge to suit specific environments, showcasing the diversity of robotic forms in service of real-world needs. Autonomous vehicles represent one of the most ambitious applications of robotics. These include not only self-driving cars but also drones, ships, and submarines that navigate independently. Autonomous vehicles integrate sensors, perception algorithms, motion planning, and control systems to operate safely without constant human input. A self-driving car, for instance, must detect pedestrians, interpret traffic signs, predict the behavior of other vehicles, and make split-second decisions about acceleration and braking. The complexity of these tasks demonstrates the integration of nearly every aspect of AI: computer vision, probabilistic reasoning, real-time control, and learning. While progress is impressive, full autonomy in all conditions remains a formidable challenge, as unpredictable road and weather scenarios continue to test the limits of technology. Human-robot interaction explores how robots collaborate with or assist people. Beyond mechanical function, robots designed for interaction must interpret gestures, speech, and emotions while presenting behavior that feels natural and trustworthy. Collaborative robots, or cobots, share factory floors with humans, working side by side without protective cages. In homes, assistive robots help elderly or disabled individuals with daily activities. Interaction design extends beyond safety to psychology, as people must feel comfortable and confident when working with robots. This requires balancing autonomy with transparency, ensuring robots are predictable while still capable of independent action. Human-robot interaction underscores that robotics is not just about engineering machines, but also about fostering meaningful and safe relationships between humans and intelligent systems. Industry has long been the proving ground for robotics, where automation has reshaped manufacturing, logistics, and agriculture. Factory robots weld, paint, and assemble products with speed and precision. In logistics, mobile robots navigate warehouses to retrieve and deliver items, while agricultural robots monitor crops and automate harvesting. These applications highlight robotics as both a productivity tool and a driver of economic transformation. However, they also raise questions about the workforce, as automation replaces some human tasks while creating demand for new skills in programming and oversight. Industrial robotics illustrates the dual nature of technological progress, delivering efficiency gains but requiring careful consideration of social impact. Healthcare represents another critical arena for robotics. Surgical robots assist doctors in performing delicate procedures with enhanced precision and reduced invasiveness. Rehabilitation robots support patients recovering from injury, providing consistent therapy and progress tracking. Assistive technologies help individuals with mobility challenges, enabling independence in daily life. In each case, AI-driven robotics extends human capabilities rather than replacing them, augmenting care and improving outcomes. The integration of robotics into healthcare also highlights the importance of safety, reliability, and regulatory oversight, as mistakes can carry high costs. For learners, healthcare robotics illustrates how AI can serve deeply human needs, blending advanced technology with compassion and care. Military and defense robotics reflect both the potential and ethical challenges of applying AI in high-stakes environments. Robots are used for bomb disposal, reducing risk to human soldiers. Drones provide surveillance or deliver payloads over contested areas. Unmanned vehicles operate on land, sea, or air, often in dangerous or inaccessible environments. While these applications highlight the protective potential of robotics, they also raise questions about autonomy in lethal decision-making and the implications of delegating life and death choices to machines. The military domain exemplifies how robotics amplifies capability, but also magnifies ethical dilemmas, requiring international dialogue and careful regulation. For learners, defense robotics serves as a reminder that technological power must be matched with responsibility. Robotics faces a wide range of challenges that limit its deployment. Power remains a persistent issue, as batteries constrain how long mobile robots or drones can operate. Safety is critical, especially in human environments, where unpredictable behavior could cause harm. Adaptability is another hurdle, since robots often excel in structured settings but falter in unstructured, dynamic ones. Ethical considerations cut across all areas, from privacy concerns in surveillance robots to questions of job displacement in automation. Addressing these challenges requires not only technical innovation, but also collaboration between engineers, policymakers, and society. For learners, these limitations highlight that robotics is a frontier filled with opportunity, but one that demands careful stewardship as it becomes more integrated into daily life. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Artificial intelligence provides the perception backbone that powers modern robots. Computer vision allows robots to detect objects, track motion, and interpret environments, while machine learning enables them to recognize patterns and adapt to new situations. For example, a warehouse robot uses vision to identify packages and learning algorithms to classify labels or barcodes. These systems must work in real time, processing large amounts of sensory input and converting it into actionable decisions. Integration of AI with perception transforms robots from rigid machines into adaptive systems that can handle variability. Without perception, robots are blind. With AI-driven perception, they can adjust to new environments, distinguish between obstacles and goals, and refine their performance through feedback. For learners, this integration shows how AI enriches robotics, bridging raw sensor data with higher-level reasoning and enabling robots to act intelligently in complex, changing contexts. Mapping and localization are fundamental to autonomous robots, ensuring they know where they are and how to navigate safely. Simultaneous localization and mapping, or SLAM, is a widely used approach that allows robots to build maps of unknown environments while tracking their own position within them. For instance, a vacuum robot uses SLAM to chart the layout of a living room, ensuring efficient cleaning without covering the same space repeatedly. SLAM relies on combining data from cameras, lidar, and other sensors to estimate both the map and the robot's trajectory. This capability is critical in dynamic environments where GPS may be unavailable or unreliable, such as indoors or underwater. Mapping and localization illustrate how robots combine perception and planning, enabling independence in environments that cannot be pre-programmed. Reinforcement learning has become a powerful approach for teaching robots new skills. Instead of being explicitly programmed, robots learn through trial and error, receiving rewards for desirable actions and penalties for mistakes. For example, a robotic arm might practice grasping objects, refining its movements through thousands of attempts until it develops an effective strategy. Reinforcement learning allows robots to discover creative solutions that humans might not design directly. However, it also requires extensive training, often carried out in simulations before transferring to physical machines. This method mirrors the way animals learn, with feedback guiding gradual improvement. For learners, reinforcement learning highlights how AI gives robots adaptability, turning them into learners rather than rigid executors of predefined instructions. Transfer learning plays a crucial role in robotics by bridging the gap between simulation and the real world. Because training robots in physical environments can be costly and time-consuming, researchers often use simulations to accelerate learning. Transfer learning techniques then adapt these skills to real-world conditions, accounting for differences in physics, noise, and unpredictability. For example, a drone might learn navigation in a simulated city before flying safely in an actual one. The challenge lies in overcoming the reality gap, where models trained in simulation may not perform perfectly outside it. Transfer learning reduces this gap, making robotic training more efficient and scalable. It illustrates how robotics leverages AI's flexibility, ensuring that progress in controlled settings translates into reliable, real-world behavior. Swarm robotics takes inspiration from nature, particularly the collective behavior of ants, bees, and birds. Instead of relying on a single powerful robot, swarms involve many smaller robots coordinating to achieve a common goal. Each robot operates with simple rules, but together they exhibit complex, emergent behavior. For instance, a swarm of drones might spread out to survey a disaster zone, communicating locally to avoid overlap and ensure full coverage. Swarm robotics offers resilience, as the failure of one unit does not cripple the entire system. It also scales efficiently, since adding more robots can increase capability without drastically increasing complexity. For learners, swarm robotics shows how decentralized AI can solve problems that would overwhelm individual machines, emphasizing the power of collective intelligence in robotics. Soft robotics explores a very different design philosophy, creating machines made from flexible, bio-inspired materials rather than rigid metal. These robots mimic the adaptability of organisms like octopuses or worms, allowing them to squeeze through tight spaces, handle delicate objects, or move with unusual flexibility. For example, a soft robotic gripper might safely pick up fragile fruits without bruising them, a task difficult for traditional rigid claws. Soft robotics challenges conventional ideas of engineering, blending materials science with AI control. They illustrate how robotics is not limited to human-like or industrial designs, but can draw inspiration directly from biology to achieve tasks that require delicacy and adaptability. For learners, soft robotics highlight the diversity of approaches within the field and the importance of creativity in rethinking how machines interact with the world. Humanoid robots represent one of the most ambitious goals in robotics, creating machines with human-like form and movement. These robots are designed not only to resemble humans but also to operate in human environments, using tools, climbing stairs, and interacting with people naturally. Examples like Honda's Asimo or Boston Dynamics' Atlas show impressive feats of balance, coordination, and agility. Humanoids appeal because they can fit into spaces designed for humans, but they also face immense challenges in balance, dexterity, and energy efficiency. While still limited in practical use, humanoid robots symbolize the aspiration of building machines that mirror human capability. For learners, humanoids represent both the progress achieved and the enormous complexity still ahead in blending AI with physical embodiment. Social robots extend beyond physical tasks into emotional and interactive roles. These robots are designed to engage with people for companionship, education, or customer service. Examples include robots that assist children with learning, provide comfort to elderly individuals, or greet customers in retail environments. Social robots rely on AI not only for speech and gesture recognition, but also for modeling emotions and adapting behavior to context. Their design emphasizes empathy, trust, and rapport, aiming to make human-robot interaction more natural. While still evolving, social robots highlight how robotics is not only about automation, but also about relationships, shaping how humans connect with intelligent machines in personal and social spaces. Robotic process automation, or RPA, represents another branch of robotics, though it exists purely in the digital realm. Instead of physical machines, RPA involves software robots that automate repetitive workflows in areas like finance, customer support, and data entry. These bots mimic human interactions with software systems, clicking, copying, and pasting, just as a person would. While not robotics in the physical sense, RPA demonstrates how the principles of automation extend beyond hardware into digital processes. For learners, it is a reminder that robotics and AI encompass a wide spectrum of embodiments, from warehouse robots to software bots, all focused on enhancing efficiency and reducing repetitive human effort. Safety and reliability are paramount in robotics, particularly when robots operate in human environments. Ensuring predictable, fail-safe behavior requires rigorous design, testing, and monitoring. For example, collaborative robots in factories must detect human presence and stop movement instantly to prevent harm. Autonomous vehicles must respond reliably to unexpected obstacles or malfunctions. Redundancy, error detection, and safety protocols are essential to building trust. Failures in safety can erode confidence in robotics, slowing adoption and raising ethical concerns. For learners, safety underscores that technical achievement alone is insufficient. Robust engineering practices and human-centered design are equally vital in ensuring robotics benefits society responsibly. Energy and power constraints present another significant limitation in robotics. Batteries restrict how long mobile robots or drones can operate before recharging, limiting their practicality for extended missions. Heavy payloads, advanced sensors, and onboard computation all drain energy quickly. Efficiency becomes a critical design challenge, pushing innovation in lightweight materials, low-power processors, and wireless charging systems. For instance, drones used for delivery must balance payload capacity with flight duration, a delicate trade-off dictated by power availability. These constraints show that robotics is not only a problem of intelligence, but also of physical resources. For learners, energy highlights the intersection of AI with practical engineering, reminding us that intelligence must be sustained by reliable, efficient power sources. Ethical questions in robotics are wide-ranging and profound. As machines gain more autonomy, questions of accountability, liability, and responsibility grow more pressing. Should a delivery robot that causes an accident be blamed on its designers, its operators, or the AI controlling it? How do we balance the efficiency of automation with the displacement of human workers? Military robots raise especially serious concerns about autonomy in life and death decisions. Surveillance robots raise privacy issues. Ethical robotics requires not only technical safeguards but also societal debate and regulation. For learners, ethics highlights the need to see robotics not as isolated machines but as actors within a human world, where values and consequences must be considered. Regulation and standards are evolving to ensure that robotics develops safely and responsibly. Governments and organizations are establishing rules governing robot safety, data handling, and accountability. Standards guide how robots must behave in shared spaces, how reliability is tested, and how liability is assigned when things go wrong. International collaboration is essential, as robots cross borders in global supply chains and autonomous vehicles operate across jurisdictions. Regulation provides not only guardrails for safety, but also a framework for trust, enabling wider adoption. For learners, regulation underscores the interplay between technology, policy, and society, reminding us that robotics must evolve within shared human rules and expectations. The future of robotics is focused on adaptability, collaboration, and intelligence. Research is moving toward robots that can learn new tasks on the fly, collaborate seamlessly with humans, and operate in unstructured environments. Advances in perception, reinforcement learning, and multimodal integration will allow robots to move from rigid, single-purpose machines to flexible assistants. We may see more integration of soft robotics, swarm intelligence, and humanoid systems, along with progress in energy efficiency and safety. The trajectory of robotics suggests a future where machines are not confined to factories, but increasingly present in homes, cities, and public life. For learners, this points to a horizon filled with possibility and responsibility, where the boundaries between AI and daily human experience continue to blur. Robotics represents the physical embodiment of AI. Where algorithms alone can classify, predict, or generate, robots take those outputs and enact them in the tangible world. They sense, plan, and act, bridging the abstract world of computation with the physical spaces we inhabit. This embodiment makes robotics uniquely powerful, but also uniquely challenging, as real-world environments resist simplification. Robots embody the successes, struggles, and aspirations of AI itself, showing what it means for intelligence to extend beyond thought into action. For learners, robotics is a vivid reminder that artificial intelligence is not only about virtual tasks, but also about machines that touch lives directly, reshaping work, care, and even companionship in society. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.